Okay. So, in theory, we have one or two more sections to talk about today, and on Wednesday, they don't have as much stuff to talk about on Wednesday. So then, the plan right now is to review on Friday, and then schedule the exam for next week. So either Monday or Tuesday. It'll be up to you guys to figure out when you want to schedule that 2-hour block on Monday or Tuesday. This has to be done during the regular business day. You gotta suck on something with my, otherwise I'll start coughing.
Okay.
So,
I apologize.
it doesn't really bother me. It doesn't matter to me whether it's Monday or Tuesday. Mondays are generally more challenging for me because we've got so many, because I've just got too many classes going on Mondays. But we're going to do it Monday. It'll just be up to each person to individually decide on when you're taking it, Monday or Tuesday. It'll be the same 2-hour test, and just have to be done by 5 o'clock. And you can start no earlier than 8. Yes.
Sorry, I know it's different class. And then thermo is this Friday?
Thermo is then the Monday after Thanksgiving.
After.
Or Monday or Tuesday after Thanksgiving.
And then what, statics that you have this Friday?
It's statics that I have this Friday. Right? Actually, they're taking it on Thursday. Yes. Okay. And I have an exam in general physics today.
Yes.
So I have
Wow.
basically a big old stack of exams to grade for the next 2 weeks.
Thanksgiving break.
Yeah, all right. Anyway. So is that okay with everybody? Everybody got that? Any questions? Any thoughts?
So we can expect to see like turkey stain on our tests when we're back.
Probably not. Probably not. All right then. Apparently,
If we do,
I've upset Mr. Orender. He's had enough.
He has some emergency poo-poos.
Yeah, it looks like it's the poop.
That's his poop level.
Can't move.
She just like clench.
Well, he's at least headed to that room anyway. Joyce is not here, right? Britton's not here. We have no idea.
He's got an interview.
There's always, there we go. Wasn't he gone last week? Oh no, Clayton's gone last week.
Okay, Clayton was gone last week, Bray's gone.
All right.
I'll let Colin know.
Yeah, well.
Colin.
I've given up.
Where is
Today we're talking about composites.
That's hard.
Now, 4 major types of composites. There are continuous fiber composites. Continuous fiber composite, if I look at the slice through, looks something like this. Right? Fibers running continuously across the entire sample.
So that, what will be examples?
Well, you can do, and you can make any number of composites. It depends on what you use, what materials you use is immaterial.
Okay, so that you can make the same
It's
material.
geometric, right? I have one kind of a fiber of one material and a matrix of another material, and the fibers are continuous and all parallel.
Okay.
Okay. Second is whiskers. Whisker doesn't, does whisker have an age?
Yeah,
I think it's with a H.
unless we talk about the cooking thing.
W-H-I-S-K.
It's a,
Whisk.
yeah, whisk. You're whisking eggs.
It doesn't matter. Okay. So whisker composite aggregates have like that. That was bad. Okay, so there you have a little short snipply. Apparently it was number 1. For anybody who was watching the video and not getting the... Anyway. Whisker composites have a randomly sort of oriented little short stubby pieces of fiber. Okay, so it's not nice and continuous and organized, they're kind of stubbing all over the place.
Like,
Yeah, there's.
OSB.
no,
What?
There's one of the materials.
Bainite.
Yes.
Bay night.
still my thunder.
Yeah.
Like,
We never had it, so.
Baymax.
And there's aggregate composites. Where we used to have big chunks. Okay. So it's randomly scattered throughout. So an example of aggregate would be concrete. Concrete is an aggregate composite. Stones, right, in a mixture of cement.
Would granite also be aggregate?
Granite is, well, I mean, at some level it is, but I mean, granite's a natural material, so it's not, it's its own thing. It's not, I mean, there are veins and stuff, but I'm not sure about the mechanical variations in there, yeah.
What was the example you gave for fiber?
Fiberglass?
Fiberglass. Okay, just like.
Sure.
This, you can also do fiberglass this way. Okay, but that's why I said, there's not a particular, you know, he asked for a specific example. The golf shaft, if you have a graphite epoxy golf shaft, it's still going to be a continuous fiber, so yes. Yeah. So there's several different combinations of materials.
Is Kevlar counted as a continuous fiber?
Kevlar is a fiber. Kevlar is just a fiber.
Oh.
Whisker, white cast iron and gray cast iron, remember me talking about those having sort of a whisker kind of formation? That's another. White cast iron is this, gray cast iron is this.
Wait, but what are the two materials?
White cast iron
Uniform.
has little whiskers of cementite.
So it's the same material, just different.
And gray cast
phases of
iron
material.
has nodules of graphite. Because it's been heat treated so that you get it to slowly form graphite instead of Fe3C. Okay? Everybody good with those two? And then the fourth kind is a weave. So we can have, within a weave, we can either have a 2D weave, in which you have fibers going one direction, and then fibers going the other direction. And usually, these are laminated on top of each other. So you have a continuous fiber layer, and then another continuous fiber layer on top of it that's the other direction. Good example of this is plywood. Right? That's what we do. That's what you do with plywood. You have the grain running one direction with one ply, and then the other direction with the other ply. So you alternate the directions to get a two-dimensional composite structure. Because as you, I'm assuming, are aware, the properties of plywood along the grain are stronger than they are across the grain. Okay. Drywall tape. You ever look at fibrous drywall tape? It's made up like this. It's crisscrossed. Right? And then the second kind is the 3D, where if I look at it from the side now, so I have a bunch of fibers running into the board here. And I have a weave that kind of does this. Something like that, and then this one does this, and, you know, that kind of thing. You get the idea. So it's three-dimensional. It's not just ply here, ply here, ply here, ply here, but they actually weave between the plies. Okay? These are non-laminated. In other words, we don't just lay down plies on top of each other. They actually, okay.
This would be like a knitting / crocheting kind of pattern.
If you want to go with that, that's fine. That works. Wood is actually this. This is what wood really is. Again, you know, creation's a lot. We got a lot more of the stuff that we try to emulate. You know, a lot of the stuff we emulate comes from what we see naturally in creation. Try to sort of emulate it, take advantage of those properties. Okay. So, and this is a relatively new thing, because you can imagine manufacturing this is really challenging. Right? These you can just lay stuff down and glue it on top of each
Yeah,
other.
so it's 2D weave, they're not actually wood, it's just more of a screen.
Sometimes you can get a 2D weave that is layers of 2D weave. So in other words, you can get like a woven, like your shirt, right? This is a woven material, and it has threads going both directions. If I lay up layers of this, that's still considered a 2D weave. It's not, even though I stack it up to be 3-dimensional, it's still considered a 2-dimensional structure. This has things going in between the layers, and maybe in between many layers. Okay? All right. The main reason we use composites is for their mechanical properties. That's the main reason we're using them. We're trying to basically bridge the mechanical properties of two different materials. So if we talk about fiberglass, the two materials are the glass, which we know has the glass fibers have a very high modulus, right? Very strong, but they're very brittle. The matrix, the thing surrounding the glass, is epoxy, so it's a polymer. So it doesn't have a great deal of strength, right? But it has some give to it. So you're trying to mix the properties of the glass, which is brittle but strong, and the epoxy, which is weaker but more ductile. And there's 3 ways that we can load it. The first is isostrain. Isostrain means all of the stuff experiences the same strain, right? Iso being the same. So if I took a 1-dimensional composite, continuous fiber composite, and loaded it in this direction, the elongation of all of the materials, both the fiber and the matrix, would be the same. Right? They would both elongate the same amount, they both have the same amount of strain. You see that, how that would be? Right? Otherwise, they just come apart from each other if they didn't. The second, as you can imagine, would be isostress. And in this case, we're just loading it perpendicular to the orientation of the fibers, so that the stress borne by the glass in this layer is the same as the stress by the epoxy underneath it, because the force is series. The force is uniform in series. And the cross-sectional area into the board is the same. Okay? The third kind is for situations where we don't have continuous fiber reinforcement, and that would be in the aggregate case, which for the most part is true for the whiskers as well. And that's just, there isn't a particular orientation, so we're just loading it. We're just loading it in whatever direction. So for an aggregate composite, there's no difference, there is no orientation, there's no specific orientation.
And that's the same for the whisker you said?
But by and large, yeah. I mean, you can actually have whisker composites where the whiskers do have a preferential arrangement. But if they're not, if they're random like this, then it would be treated like there. Okay, so we're going to look at each of these quantitatively. So we'll look at isostrain first. So we have some height of sample that we're starting with. We're applying the load P. So the strain in the composite is equal to the stress in the composite divided by the modulus of the composite. Similarly, the strain, in the fiber is equal to the stress in the fiber divided by the modulus of the fiber, and the strain in the matrix is equal to the stress in the matrix divided by the modulus of the matrix.
What's the composite versus the matrix? What's
The whole thing.
the composite whole thing?
The fiber is just zooming in on a fiber, the matrix is zooming in on a matrix. And because it's isostrain, we know all three of those are equal. So, but because they're oriented in this way, the load borne by the composite is the sum of the load borne by the matrix and the load borne by the fiber. And it's like, you can think of it as a bunch of springs in parallel. Right? They're each bearing their own respective load. The total load is the load shared by the stress. And so that means then that the stress in the composite times the area of the composite is equal to the stress of the fiber times the area of the fiber plus the stress of the matrix times the area of the matrix. Load is the product of stress and area.
That's what P is. P is load.
P is load, right? Come over here.
Oh.
And we know right, for anything, stress equals modulus times strain. So we put all these together and know that modulus of the composite times the area of the composite times the strain of the composite is equal to the modulus of the fiber times the area of the fiber times the strain of the fiber plus modulus of the matrix times the area of the matrix times the strain of the matrix. But the strains are equal, so they can cancel out. So we can solve then for the modulus of the composite, right? That's really what we want. We want the properties of the composite material. Just by dividing through by area. So that's EF AF plus EM AM divided by AC. Right? Make sense? But they all have the same height. Remember, area here is the area of that end face, the cross-sectional area. They all have the same height. So I can rewrite this as EF times the volume of the fiber plus E of the matrix times the volume of the matrix divided by the whole volume of the composite. Because typically that's what we measure. Right? We figure out, we can know how many fibers we put in, what the mass of the fiber is and the density of the fiber, we can find out its volume. And in fact, the way you're most likely to see this is EF times little vf, which is the volume fraction, plus EM times little vm, or little vf is the volume of the fiber divided by the total volume of the composite. It's the percent, basically the volume percent of that component.
That's because VC is basically just VF plus VF.
Yeah. So, for an isostrain condition, the properties of the composite are just the weighted average, the volume weighted average of the properties of the two individual components. That make sense? Yeah, pretty straightforward. And typically, actually, one of the other things that we really are most concerned about, if you think about it, when these things are put together, what do you think is what is going to break first in an isostrain configuration?
The fibers.
Yeah, the fibers are gonna break first, right? Because if it's isostrain, and the stress strain curve for the fibers looks like this, and the stress strain curve for the matrix looks like this. Right? The matrix can stretch, it's epoxy. But it's isostrain, we're only gonna be able to go until one of them breaks. Right? The fibers can't exist beyond that. So what we really are often most concerned about is what load is being borne by the fibers. Right? We want to know not just the overall properties of the material, we want to know how much load is being borne by the fibers, because it's the first one that's going to break.
Are we just assuming that the material of the fibers is a steeper slope there than the material of the?
That's, you know, you make composites with a strong, high modulus reinforcement and a low modulus matrix. That's just, that's where the benefit comes from.
Otherwise, I mean, you would, great.
Right, if you had a high modulus matrix, then you just use the high modulus matrix. It doesn't, you know what I'm saying, it doesn't buy you anything. Right. So, sometimes of greater concern is the load in the fiber divided by the load in the composite. What fraction of the load is being borne by the fibers? Okay. So if you go back to the original, that's going to be sigma F AF over sigma C AC, which, if you play it out, essentially becomes EF over AC times the volume fraction of the fiber.
What would you do there?
I just did the same thing as I did here. So each of these becomes EAE, and then the E's cancel out because the E.
Yeah, why are we taking the ratio of the loads though?
We want to know what fraction of the load is being borne by the fibers, because the fibers are the ones that are going to break first.
Oh.
Okay. And it turns out that this does not just apply to elastic modules. In general, other properties, thermal conductivity, diffusional constants, all that kind of stuff. There's sort of this generic format that the property of the composite is equal to the volume fraction of the fiber times that property of the fiber plus the volume fraction of the matrix times that property of the matrix.
I think I missed something where you start dividing by the volume of the composite.
I just distributed the VC into VF and VM. So that I've had the volume fractions, the volume of the fiber divided by the volume of the composite.
Oh, so you redefine VF?
This is
Oh,
a
that's
little
a little
v,
v, okay.
that's a capital V.
Yeah.
Okay. So essentially, in an isostrain configuration, the properties in general of the material are the weighted average of the fiber and the matrix, or fiber and the matrix. What?
None.
And you'll find that that's therefore the way that we typically use composites. Right? We design the composite to take advantage of the isostrain configuration. But we have to be aware of the isostress because it still exists, right? I mean, I have a fiberglass hull on my boat. It's going to experience stresses in both directions. I may try to design it so that the larger stress is in the isostrain configuration, but it's still got to be able to bear lateral load as well. So I've got to be able to look at isostress as well. Okay, so now we're using the same conventions here, although I'll call this LC instead of H. So for isosтрess, we know that C equals sigma F equals sigma L. Again, in series, the load is the load is equal in series, just like the displacement is equal in series. So, but now the strain, the elongation, delta LC, is equal to delta L of the fiber plus delta L of the matrix. So the total elongation is the combined elongation of each of the individual components. Now I'm going to define an area fraction same as the volume fraction. Right? Follow me? So the length of the matrix is equal to the area, lowercase a. Area fraction of the matrix times the length of the composite, and the length of the fiber, area fraction of the fiber times the length of the composite. We can figure out how much length is in fiber by adding up the area fraction or the volume fraction, assuming uniform properties throughout the thickness. I use the volume fraction just as easily.
Volume and area fraction are equal.
As long as everything's uniform in the third dimension, right? So here we assume everything was uniform into the board. You know, they all have the same thickness, or the same distribution is the same, right? Or through the H in this case. We used the area fraction on the top end and then assumed it was uniform through the height. Here, we're assuming it's uniform this way, right? And then the area fraction's the end face here. Okay? But it could be, like I said, so it could be volume fraction or area fraction. So we know what's the strain of the composite. How's that defined?
Delta L over L.
Yeah, delta L over L. So it's delta L sub C over L sub C. And the strain of the fiber is delta L of the fiber over the initial length of the fiber. And the strain in the matrix, delta L of the matrix over the initial length. Okay, so now we can wrap it all together. Plug in here for L sub M and L sub F, and we get that the strain in composite is equal to the area fraction matrix times the strain in the matrix. All right, everybody see that? Plus the area fraction of the fiber times the strain in the fiber. All right, so I've gone through and basically taken delta LC, this top equation here, divide through by LC, right? So delta LF over LC is this piece, delta LF over LF times LC over L, or LF over LC, which is AF. You with me? So, epsilon sub F is equal to delta L F over LC times LC over LF. Right? LC over LF from up here, this piece, right, is 1 over A. Oh, shoot, that should be 1 over. LF over LC is
It's
AF.
LF over LF. Delta LF over LF.
Oh, right.
I know where you're going.
Delta LF over LF, that's right.
Yeah, that's
right? Nuts. So this should be. What did I do?
Oh. Equals 1 over A times
Yeah, but that's,
12th of N off over LC is useless.
yeah.
What do you get? LF for LC.
So I'm plugging that back in. Oh, no, that's it. That's what it was. No. That's what it is. It's this equation I'm trying to solve for. Right, sorry. Delta LF over LC is delta LF over LF times LF over LC. There we are,
So
to get to there.
that's the actual real equation, not delta LC equals delta LF plus delta LM, are they both correct?
Right, so this is epsilon sub C equals that plus delta LM over LM times LM over LC. So essentially dividing through this whole thing by LC. The left side here is E sub C, the epsilon sub C, it's the strain in this composite. And then I just have these other two pieces in here, which become AF and AM. There we go.
So does delta LC equal delta LF plus delta LM?
Mm-hmm.
So that's
Right,
true,
right, so this
and
is,
what
this
you
is
wrote
true,
in now.
right, if I elongate this, it's the change in length of each of the two combined.
No, that makes sense.
Okay, straight, the elongation is additive in series, and load is additive in parallel. Okay, so we're back to, anyway, so back to this thing. And that's then equal to A sub M times, well, epsilon sub M is sigma sub M over E sub M. Right? Which is equal to sigma of the composite divided by E of the composite.
It's sinking. Proof.
No.
Delta the composite equals E the composite.
There were words that were spoken, and I can mimic them back. I have no idea what we're talking about, but I can at least repeat the words that were spoken. Okay. But we know that the sigmas are all equal. So I can cancel them out. And what I'm left with then is 1 over EC is equal to AF over EF plus AM over EM. Or, again, I can do it in volume fraction. VF and VM. We assume the properties are the same all the way across.
It's like electrons.
Right? So yeah, just exactly. Capacitors and resistors, series and parallel, right? It's all the same kind of stuff. Right? It's exactly the same concept. So that what we end up with then is EC is equal to EM times EF over the volume fractions. VM times EM plus VF times EF. Just inverting.
That V is the fraction thingy.
Volume fraction. Yeah. Fraction thing. Right. So, the more general expression then, put it down here, is x sub c is equal to x sub f times x sub m over b sub f, x sub f, plus b sub m, x sub m. For other properties, things that are not. Excuse me. sense? Again, series and parallel. These are parallel, these are series, right? Capacitance, measuring here. So capacitance in parallel adds directly, capacitance in series adds inversely. Make sense? Load bearing capacity.
Load bearing capacitor.
Yeah.
Bad structural source.
What's that?
The load bearing capacitor sounds like a bad structural source. Usually, like a massive capacitor, like actual electrical capacitor, making your beam like an exact position.
Okay. Whatever it takes to get it through your head, I suppose. Is what matters. All right. So that leaves us with one more configuration. Everybody okay with isostrain and isostress? Now we're left with one more. But you notice that there's a theme here. What's that? There's a theme here that x sub c is equal to the n is equal to v sub L x sub L to the n plus v sub h x sub h to the n, where L is the low modulus material and H is the high modulus material. Right, it's the same format for both of them. Right? E to the minus 1 equals Vf times Ef to the minus 1 plus Vm times Em to the minus 1. Or x to the plus 1 equals Vf times x to the plus 1. Right? So we used to have a difference here. We have negative of n values of 1 for isostrain and n values of minus 1 for isostress. You see that? So essentially again, isostrain n is equal to 1 isostress n is equal to minus 1. So if we plotted those out, on the horizontal axis I'll have the volume fraction of the high modulus material. So over here, and we're going to plot modulus, but it could be whatever property. X is the low modulus. If we have zero high modulus material, the modulus of our composite, such as it is that of the low modulus, right? It's all epoxy. Over here, if we have 100% high modulus material, it's going to be sub H. Okay? N equals 1 is a straight line. That's what the isostrain condition represents. N equals minus 1 is kind of like that. You see that? Okay. So with aggregate composites, if we have a high modulus aggregate in a low modulus matrix, that corresponds to n equals 0. Which would be somewhere like that. modulus aggregate in a high modulus matrix that corresponds to n equal 1, which, as you can imagine, is then between n equals 1 and n equals 0.
What would be one, like, what would be an example of a low modulus and high modulus matrix?
A low modulus aggregate in a high modulus matrix. It's not a common approach, but I'm trying to think of, I don't know if I'm aware of a real life scenario in which that would happen.
So then that, like, n equals 1/2 isn't very common in life then?
So, yeah, I'm not sure about the relative moduli of various aggregate composites. I mean, you can think of titanium dioxide in glass to make it opal glass, or to make a cloudy glass. I have no idea whether where the relative moduli of those two things rests. Okay. I'm assuming that concrete would probably be n equals 0. That the stone that is used in concrete probably has a higher modulus than the cement.
Right, if n equals 0 on that equation, then that just means BL equals VH minus VH.
If n equals 0,
Then XC equals VL plus VH.
it just means BL plus VH equals 1.
Or, yeah, right. How's that useful?
Well, I mean, really, which we know, right? You'd actually probably wouldn't solve it that way, would you? Yeah, I'm not sure how you mathematically would that. I mean, this is not the way that you would express that. But the bottom line is, for any of these things, right, if we're in isostress conditions, or maybe even if we're in a high modulus aggregate and a low modulus matrix, so either of these two, we've got to have a pretty high fraction of the aggregate in order to significantly alter the property. Right? Everything from here down, right, down in here, we really not change the properties much from the low modulus material. So we have a low modulus aggregate in a low modulus matrix, or in the isostress condition, the low modulus, whichever one it is, it doesn't matter, because they're not the same distinction there in terms of aggregate or matrix. But the low modulus material, you've got to have a lot of high modulus material in order to significantly alter the overall modulus. But in an isostrain condition, you've got the best chance to alter the properties of the material by adding in modulus, or by adding in reinforcement. And so here, if I go halfway, if I go 50-50, I've significantly altered the modulus here. I haven't really significantly altered it
So you're more like 80 or 90% of the higher modulus to get up to that 50%.
there. Right, so if I want to, if I want to improve my modulus by 50%, right, I got to get up here to 80 or 90 to do it in that direction. I got to be maybe 50, I don't have to be 50% to get there. So that means that when I look at my fiberglass that's all running in the same direction, the lateral properties are basically epoxy. And this one is the one that's really significantly if it's a 50-50 mix. And you can actually improve it better than that by actually using a lot more. In fact, that's what this is, right on the front cover of your book. That's a composite. Right, you look at the volume fraction there, there's a lot of fiber on there. Well, maybe not on your book. But for the rest of us, that's what's on the front of your book. It's a two-dimensional, it's not a weave, it's just a laminated structure. Right, so it's a layered, two-dimensional composite. But hopefully you can kind of get the gist by looking at that there's a significant volume fraction there that's fiber. Right, that presumably is the stronger, usually the stronger material, higher modulus material. Okay. So it's something like that, if we're up here to, in this kind of ballpark, then we've got higher properties in both directions. And in fact, in this one, that's why you weave them like this. Right? So some of them are isostrain and some of them are isostress. So we average the properties of these two. Right, so if we're at 90%, and we have a one-dimensional weave, we have a really strong product. If we have a two-dimensional, or the isostress conditions, it's not so strong. But what we end up with if we do a two-dimensional weave is we end up with that property in both directions. Yeah.
Is it ever possible to get an N greater than 1 or less than -1?
Is it ever possible to get an N greater than 1 or less than, I don't know.
Okay.
I'm not familiar with any.
Maybe it's like that, you know.
I don't know why you'd want anything less than negative. Right? I mean, I suppose there could be some kind of nonlinear material that would give you an N greater than 1. But I'm not, you'd have to be.
We're not
It'd be
gonna
like
make it
non-Newtonian, it's like a non-Newtonian fluid, you can get weird behaviors, but it's not realistic. Any questions? You have no questions?
That's rare.
What do you ask them?
That's because Joyce isn't here. She's usually the one who's going off. All right. Then there's another minute of your life back.